So first of all, I want to thank everyone for taking the time to show up to today's lecture. This really means a lot towards me and Alex because this aligns greatly with our research focus at UVA. So this is something that we're really passionate about, and we're excited to share this knowledge with the rest of you guys. But yeah, with that being said, this is Transformers from a mechanistic interpretability perspective, and this will be part one of a three-part series. And so today, we're going to be focusing on mathematical intuition for transformers.
Okay, so we wanted to start off with some motivation, because this is a little bit different than the traditional way that you would teach transformers, right? So typically, traditional approaches for teaching transformers, they don't prioritize the why as much as the how or the what. And what I mean by that is that it typically leads to an explanation, of the mechanism of transformers, right? Literally, what's happening inside of them, what are the operations, what's going on, but without really distilling a deeper understanding of the intuition behind that mechanism to the learner. And the result is that this way about teaching transformers will often lead to a lot of confusion, and the process is just more difficult because without an intuitive understanding of the motivation behind why we're doing these things, these processes, they can seem random and they can seem arbitrary.
Yeah. Throughout this lecture, we want to put you guys in the position of the researchers who came up with this architecture, and by that, we want to be able to give the motivation for why we do things that we do. Right, and so that basically brings us to this research area of mechanistic interpretability, right? And these next couple of slides, just quick overview, general logistics for our lecture today. So mechanistic interpretability is a field of research that's dedicated to reverse engineering and thoroughly understanding the inner workings of machine learning models, right? And the main idea is we want to be able to understand, how machine learning models work. And we don't like the idea that most people say that it's a black box, right? We want to be able to create a method to the madness that's machine learning.
Exactly. Yeah, so let's talk a little bit about knowledge distillation. In this case, not in the machine learning context, but in the human learning context, right? And the core idea behind this really is just because something is advanced and complicated doesn't mean that it has to be difficult or confusing to learn, right? The truth is that everyone is better off when information is more accessible, right? Especially machine learning. Why do we do machine learning? I think most people who do machine learning don't do it because it's so beautiful, right? And people do it because it's useful, right? Machine learning is going to be one of the most impactful technologies of definitely these few decades, probably this century too, and we're already definitely seeing that, right? And because of this, we cannot view it science, as some exclusive art, but instead we need to understand, we need to know, we need to believe that the inclusivity and the accessibility of this science is vital for the most beneficial human progress. Just a quick note, we strongly agree and take inspiration from the viewpoints expressed in the paper research debt within the distilled journal.
And part of the lecture today is focusing on giving a mathematical intuition for transformers, right? It's part one. And so we might be wondering, why are we worrying about math in a machine learning lecture, right? And the reason for that is because while computer science is the way in which we implement machine learning models, the foundations for understanding machine learning always boil down to rigorous mathematical concepts. In other words, if you want to learn the science of machine learning, if you want to learn, how and the reason why we do things that we do in machine learning, you will always keep asking yourself the question why. And why will always take you down to some type of basis in math. So we first need to understand the mathematics that she rests upon.
It's a question. So we will pause frequently for questions. And furthermore, if you have questions at any time, please do not hesitate to raise your hand and ask. We strongly encourage you to ask anything that you are confused about. We really don't want people getting having questions and getting confused like 10 slides in, and then they don't even know what we're talking about now, right? We want to make sure that you understand what's happening. So once again, please feel free to raise your hand and ask questions.
Okay, so let's talk about table of contents, right? So we're going to first talk about briefly what do transformers do? What's the goal of LLMs? Very, very briefly touch upon this. We're going to come back to this in the next week's lecture. Then we're going to talk about vectors and vector spaces and how to work with them. We're going to talk about linear transformations. Then we're going to naturally segue into the concept of word embeddings. Then we're going to talk about a really cool, neat hypothesis about these word embeddings. And then finally, we're going to talk about the essence of what the transformer is really doing in a mathematical sense. Cool.
So briefly, what do transformers do? So, okay, so in this presentation and in this series, we're mainly going to be talking about transformers as language models, right? So the architecture of transformers, it's one of the, it's the one behind most large language models in use today, like ChatGPT, Cloud, BERT, and Llama, right? And these were originally developed for language model use. They have since found applications in many other fields, such as vision. Nonetheless, in this series, we will focus on them from a language modeling perspective.
Right, so basically, I guess the question is, what is language models, right? Or what are language models? So language models are any machine learning models that are used to understand, make predictions on, or inferences upon human language. In other words, if you have any given language task, right, you want to predict the next word in a sequence, you want to do sentiment analysis, what's the emotions or the emotional valence of a word. If you want to do any language task at all and use machine learning to solve it, well, the chances are that you're working with a language model to do it, right? So here's some examples of things that language models can do. Next word prediction. I was hungry, so I went to the natural follow-up there is restaurant. That's what a machine learning language model will predict. And then calculating emotional valence and predictions regarding that. This is the best experience of my life. It might be, semantically related or, sentimentally related to positivity, so on and so forth.
All right, so then we'll move on to the first mathematical section, which will give a brief overview of vectors and vector spaces. So we'll start off with vectors, right? What are these? Well, vectors are an ordered set of values representing a direction in a certain space. For example, within a 1D space, a single value, just one number, is a vector, right? And what is a 1D space? Well, that's just a line, right? So we have this number line here, right? Then the value or the vector, that's just one, represents the direction that goes from 0, which is the origin, to 1. Similarly, in 2D space, two values are vectors, right? So say we have this 2D space here. Then if we want to represent the direction, that goes 3 in the x-axis and 2 in the y-axis, then we can represent that with the vector 3, 2.
So similarly, a vector space is a space where vectors of a certain dimensionality can be scaled and combined. So what does this mean, right? If I had a two-dimensional vector, then we're going to say that it belongs to a 2D space, right? So we want to imagine that this 2D vector is sitting in this vector space, of other different vectors that are also inhabiting it, right? So for example, the vector phi, 5, for example, the blue vector over there, would be such a vector in a two-dimensional vector space. And then the other one, -1, 5, for example, would be another vector in the two-dimensional vector space. In fact, any vector that you can think of that is two-dimensional, if you combine them all together, you get this huge two-dimensional blowout, right? that two-dimensional, that's what I'm talking about when referring to a two-dimensional vector space. So vector spaces could be of any dimensions. As human beings, we can only ration about them in a maximum of a three-dimensional space. So a three-dimensional space, for example, this is an example of what two such vectors or two elements of the vector space could look like. So an n-dimensional vector space is a space where n-dimensional vectors live and where they can have, yes.
So could you have like 2D vectors in a 3D space?
Yes. Well,
Sort of. So the moment you have a 3D space, right? And so imagine you have a 3D space, and then you have a 2D vector in that space, right? What that probably means is that there's one dimension of the 2D space, or there's one dimension of the representation of that vector that's 0, right?
yeah.
But that's still a 3D vector.
Yeah.
Because you can represent it as a 3D vector.
And we'll talk about this.
Basically, the n-dimensional also counts as a 1, that's correct? Because in here, if you go back to the previous slide, you show like a single value as a vector, but in the next one, you said n-dimensional. So n-dimensional counts from 0 or 1 until so on, or how is that? Because I don't see what is the range when you mean dimensional?
Yeah, exactly. So the number of dimensions can range from 0. And when you have 0 dimensions, that just means like a single point that can't move anywhere. Yep, and then you can have, however many more dimensions you want.
And then in each dimension, so if you have n dimension, you represent this as a vector that has n different numbers.
Yeah. Humans, it's really hard for us to picture, dimensional spaces that go beyond 3. But you can have however many you want to, 10, 100, 7 billion.
Okay. And to go back to your question, you can have, you can have a three-dimensional vector, only three-dimensional vectors into 3D space, but you can always project them downwards sometimes. Or you can always project them downwards. I'll talk about them in a bit. Right, so that brings up a good point, right? This concept of subspaces, right? So a subspace is a lower dimensional vector space that inhabits a higher dimensional vector space, right? So initially we talked about a 2D vector space as kind of like a plane, right? Then we can think of a 3D vector space. If we imagine a plane inside of it, then that plane is a subspace of a three-dimensional space, right? In the same context then, even a line in 3 dimensions, even a line in 2D space would also be a valid subspace of a three-dimensional space, because in itself is in its own right a vector space, just in a different dimension.
All right, dot products. So this is a mathematical operation, and which is also referred to as the cosine similarity or the scalar product. And so we're not going to cover how this can be or how this can be computed here. Basically, this is a way of multiplying two values to produce a scalar, which is just one value, a single number, right? And one important property about the dot product is the more the vectors point in the same direction, the larger the value. And what that means is, for example, say that we have two vectors here, right? The blue vector and the orange one. If the angle between these two vectors is less than a right angle, it's less than 90 degrees, then the dot product will be positive. If the angle between these two vectors is 90 degrees, then the dot product will be 0. And if the angle between these vectors is greater than 90 degrees, then the dot product will be negative. The dot product, or the magnitude rather, the value of the dot product will also be influenced by the magnitude of these vectors. So if you have longer vectors, then your dot product will be larger.
Yeah, and the main takeaway once again is that the closer those vectors are, right? The more they point in the same direction, so the closer that they are, the higher that value is going to be.
Exactly.
Like he said.
Pause for questions. Yeah. Does anyone have any questions? Fantastic.
Cool. Okay, so let's talk about linear transformations, right? And then before we talk about linear transformations, let's talk about the concept of linearity, right? So it turns out that linearity has a couple of really cool or really nice properties that we really care about, okay? And the first is that if you have two linear transformations, right? or two linear projection transformations, then by applying one right after applying the other, you can basically think of them as one entire linear transformation, right? So for example, if I took one vector and I linear transformed it into another vector, and I linear transformed that into another vector, then that third vector can be represented as the linear transformation of the first vector. And we can easily decompose any linear representation that we have into components, right? And it makes a lot of interpretable sense for us to perform operations such as adding or scaling when we have linear representations that we deal with. So in other words, because of the simplicity of linearity, linear relationships are really easy to understand and they're really easy to interpret. And we'll talk more about what linear transformations are on the next slide.
Yeah, exactly. We haven't covered that yet. We just wanted to motivate it.
Yeah.
Okay, so first, before we talk about what linear transformations are, let's first talk about what transformations are, right? Specifically transformations on a vector space, which we typically just refer to as transformation. So this is a function which acts on vectors inside a certain vector space. For example, a transformation on a 3D vector space is a function that changes 3D vectors, right? Now, transformations can either retain the dimensionality of the vector. So you can have a transformation which takes 3D vectors and turns them into different 3D vectors. They can increase the dimensionality and turn a 3D vector into a 4D vector, or they can decrease it. You can turn a 3D vector into a 1D vector.
Right. And the main idea is that this transformation is linear if it satisfies two key properties. Okay. The first is that it has to preserve vector addition. The second is that it has to preserve scalar multiplication. Okay, so what do I mean by that? Imagine I have two vectors, okay? And these two vectors are parts of the vector space that we talked about before, right? So we have two vectors, let's say they're two three-dimensional vectors. And I add these two vectors together. Now I have the sum vector. If I take my transformation and I transform it into a vector of another vector space, right? Then that's the same as if I independently transform those two separate vectors and apply that sum in the other vector space, right? So I can sum up the two vectors, transform them, or I can transform each of the components and then add them together. Similarly, with scalar multiplication, I can multiply a vector by a scalar, then transform it to another vector space, or I could transform it to another vector in a vector space and then scale it by that same value. And these two things are completely equivalent. And this is what I was talking about when I said earlier that this linearity makes it really easy to interpret and understand, because we know exactly how transforming vectors or how transforming a vector space has an effect, right? And by composing two linear transformations, one after the other, you'll find out that it itself is one entire linear transformation.
Exactly, and just to add on to that, specifically regarding the concept of decomposing a linear representation, and this is very, very broad. But say that you had two vectors, right, and both of them mean something, right, and then you did some transformations, some linear transformations on the sum of those two vectors, right? Now you can do however many linear transformations you want, but since compositions of linear transformations are still linear transformations, then we know that this first equation must be true, which means that we can then decompose the result back into the individual contributions of these two vectors, and this can be very powerful when we're trying to interpret what models do.
And build them up, we can split them down.
Exactly. All right. So these following cases and combinations thereof are on vectors in a vector space are linear transformations. So basically, these are the first four here. These are basically like the basic building block linear transformations, and with combinations of these linear transformations, you can create make all possible linear transformations. So they are scaling. That means you have some vector space, right? And then you find some direction, and you basically make that direction larger, or you make it smaller. And don't worry, we have visualizations very soon You have rotation, meaning you just rotate things around. You have reflection, meaning you find some direction, and then basically things that they will basically reflect across that direction. So things that are positive are now negative in that direction. And you have shearing, which is a little bit harder to describe. But again, we'll have a visualization soon. Yeah.
So reflection can be understood like a mirror.
Yes, exactly.
Exactly.
Exactly. Yeah. And then finally, you have the projection, which can can be defined as a combination of the others. But the reason that we mention this is because when you have a linear transformation, which reduces the dimensionality, which is going to end up to be a very important concept. Those are done via projections. Yeah, so here we have some visualizations. So this is scaling, right? We're stretching in this case this direction, the x direction. We're going to make it longer, or you can also make it smaller. We have rotation, so just take the whole space and you rotate it. We have reflection, which is exactly like mirroring. And then we have shearing, which is this funky motion here. And finally, we have the projection, which collapses or reduces the dimensionality of this vector space into a subspace. In this case, we're going from 2D to 1D.
Yeah, and these are all 2D transformations on 2D.
Yes.
But they generalize to ND.
Yeah. All right. Questions?
Okay. Did we lose anyone? Yeah. Are we good so far?
I like the visualizations.
Yeah.
So were there any of those that you said like you could increase the dimensionality of vectors with transformations? Were any of those ones that could do that or no?
So basically, the way that you increase, so the way that things can be increased, right, is, for example, say that you have a 2D or a 2D space, you want to increase it to 3D, right? Basically, like just picture that suddenly you have a 3D space, and then you take some plane, and then you put it however in that 3D space you want to.
Exactly.
And then everything from that 2D space that you had is just then put onto that plane. And now suddenly you've increased the dimensionality of those vectors. Then you can do further linear transformations on those vectors.
So any smaller dimension vector space, you can think of it as like as part of that larger dimensional vector space, right?
Yeah.
So because of that, like you can just basically project it upwards by placing it however you want into that place.
I think actually this helps. So say that we have this, right?
Yeah.
So first say that you start with some 2D space here, right? And you want to put this into a 3D space. You want to increase the dimensionality. Well, just take this 2D space, along, with the vectors here. And then you impose that 2D space
upon the
onto
three-dimensional
this plane,
vector space.
right? But you put it onto this orange plane here. And suddenly now, the subspace along with its vectors are now in 3D space. Great question.
Like I was saying before, you could have a three-dimensional vector, right, that you can project into two dimensions the same way, by collapsing that down.
Yeah.
Yeah. Okay. More questions?
Cool. All right, let's talk really quickly about matrix multiplication. We're not gonna go into too much detail, but the main idea is that multiplying by a matrix is the same as applying the linear transformations that we just talked about, right? So say I had some vector, okay, and I multiply on the left-hand side by some matrix, okay? The output is a new vector that's the transformed version of that initial vector, right? So we initially talked about T of V, right? We take vector, we pass through linear transformation, we get a vector in another vector space. Well, that's exactly what happens when you multiply by a matrix, right? We take some vector and then we send it to another vector space, right? And we send it to another vector in a vector space. So as long as we're concerned today's lecture, or in subsequent lectures, any matrix multiplication is a linear transformation. And by that respect, by multiplying by a matrix, we can rotate, we can shear, we can reflect, we can do all those project, we can do all those things.
Right.
Okay, the fun part.
Yeah. So we have a question for the audience, right? Fundamentally, machine learning models can only understand numbers, right? Because you use numbers, right? So the question is, how can we build a model which can understand letters, words, and sentences? And please feel free to take a moment and think about this.
Do you mean tokens? We use tokens to make the model understand?
Yeah, so you can use tokens, right? But
Yeah.
tokens still, represent, words or parts of words. So how do we turn that, or how can the model, how can the model understand what the tokens mean?
Any other ideas from the audience? Okay, Rafi.
Can we map each token to a vector and then do linear transformation stuff?
Very good.
Nice. Okay, so, right,
Yeah.
I guess we move on.
So the idea is, for example, with word embeddings, we use these kind of transformations that the algorithm will understand what is the meaning of the closest meaning.
Yeah.
Correct. Yeah. So, all right.
Yeah, so basically the idea is the model only understands numbers, right? So that's what we'll do. We'll give the model numbers, okay? We're gonna give the model enough numbers as it requires to represent the meaning of that word, all right? We're gonna represent each word as a high dimensional vector. So think a really long vector, still with numbers, right? And for example, the original BERT model, which is an example of a transformer architecture, actually used 768 dimension long vectors to represent its words, okay? GPT-3, the thing that we use for our math homework, right? It uses 12,288 dimensions, right? So each word will be mapped to the same, 12,000 dimension long vectors. So yeah, we give it a really long vector to give it more space to understand nuance, right? More space to understand concepts. And we'll talk about how this happens.
All right, so first we'll just make a quick definition, right? Vocabulary is just the set of all the words that we, or the model rather, recognize, right? So for example, in this case, our vocabulary could consist of just these 20 words, which we'll try to teach to the model.
Yeah, so it's just these words is the dictionary that the model has. It's only words that exist in the English language as far as the model is considered. Right? In reality, this vocabulary will be really large. Every single word in the dictionary, right? But for now, for simplicity's sake, we'll go with this. Okay, and ultimately, we want our model to learn and generalize to language tasks, right? So what we're trying to do here, yes.
Sorry, before you move on, could you define what you mean with generalize?
Yes, so by generalize, I mean that it's not just going to memorize how to do a certain task, okay? It's going to understand the very essence of what it means to understand language, right? It will understand and learn patterns that are necessary, to accomplish certain tasks, right? For example, if I ask you a question right now, right, you would respond, given some coherent sentence, right? But the sentence is not pre-programmed. You learn how to respond to questions. You learn how to answer general questions in that regard, right? Or if I asked you, to solve a math problem, right? You may not have solved that math problem before, right? If I asked you to solve 366 plus 465, you would give me the answer, but you haven't solved that specific problem before, but you generalize to the task, so you can solve something you haven't seen before. You understand the essence of math, not just the specific problem that I gave you. To translate this to a language task, it's the same thing. We want to understand the essence of language and not just a specific language task. It must understand how grammar works. It must understand that, how to persuade an audience, if you will, to respond in a way that persuades an audience, if you will. right? It must understand what positive words are, what negative words are, and not just memorize that happy is always a positive word. Doesn't it make a little bit more sense?
Yes, yes, thank you.
Okay, so ultimately, we want our model to learn a language, to learn and generalize to language tasks. How do we do that? Well, how do you learn the language? Well, language is just patterns, right? Language is built upon some type of semantic, syntactic, and contextual patterns that we have, right? So we want our model to learn and generalize to the patterns of language, okay? So what does that mean? Well, embeddings is everything we know about words, right? Like if coward means something in our English language, the assumption is we want these embeddings to also reflect that same understanding, that same meaning, right? So if our words have a certain pattern to them, have a certain nuance, and have a certain relationship with them, we want the same relationship to carry over with our embeddings, right? Like if I think that burger, sub, hoagie in my mental mind map of how I view words as a human being, I group words together based on their semantic syntactic similarity, right? All plural words might go together, all sandwich burger related words would go together, all the bird words would go together, hero, Spider-Man, Flash words would go together, stuff like that, right? So then in my embedding space or my vector space of the different embeddings that I have, right, that I create, each of the embeddings must also carry that pattern and that nuance too. So yeah, so words that are semantically or syntactically similar should also be close together in the embedding space that we create. Does everyone kind of understand, I guess, what we want from our embedding space, how we want it to behave? Yes.
When you're giving like a prompt to an LLM, how do they differentiate between terms and like individual words? Like I see like Alex Ning there, like how does it know that that's one entity versus like separating them?
That's a good question, right? And it goes back to a previous question by one of our audience. The idea is we don't just give the words itself to the model, we give something called tokens, where we kind of define, what is one token, right? So for example, in this case, Alex Ning is a token, right? It's one word.
So that in our vocabulary, it's
Yeah, well, okay. As human beings, we have learned the relationship that human names have a first and last name.
Sure.
Okay, but there's nothing necessary that says the model must learn the same thing, right? So in this case, in this example, we are kind of chunking it together as one entity, right? But you can imagine I can also tokenize different way. I can also have two separate, Alex, I can have a name, right? And it might learn over time that those two things go together because they've been used together so many different times.
See, another way that maybe we can interpret this is, okay, we have like a pool of words and we try to match the closest, based on a token, we try to match the closest word in this pool. It's kind of like the conditional probability words in this, this is more advanced, but it's kind of that words in this autoregressive model like GPT, that it will be accurate to say that?
Yeah, and I think I'll one-up that, right? Because words that are similar together will be close together, what you're saying, right? But it's not just words that have same semantic similarity, right? Similarity can be generalized to different things, right? Words that have similar grammar, words that might go really well together depends on, a certain like feature that we'll talk about in the future, right? Like if my task is to predict whether or not a word was positive or negative, sentiment analysis, then it does not. Then I wouldn't want burger and hoagie to be next to each other based on their meaning purely. I would want words that are positive to be closer together, right? So there's some more nuance there to exactly how this embedding space reflects the relationship between the words. But for now, the main idea is we want to start bringing these relationships into our embedding space, our baby embedding space that we have right now, right? You want to add on to that?
Yeah. I think that's a great point. So, it turns out, yeah. So, for example, we saw, that GPT-3 used a huge, or the embeddings for GPT-3 were huge, right? And you have 12,000 different dimensions. And it turns out that when you increase the number of dimensions, the amount of available space that you get doesn't scale linearly, but it scales exponentially, right? And what ends up happening is, with these models that have tens of thousands of dimensions, basically the available space for them to store knowledge within the embeddings is massive, right? And for example, like you may not only, end up storing things, like semantic similarity or syntactic similarity, but also world knowledge, right?
Yeah.
For example, I don't see a particular reason why blue car is, or why blue and car should be that much more similar than red and car, right? But there is a reason why white and house is a lot more similar than blue and house, because the white house, that's world knowledge. The particular term white house comes together a lot more often than blue house, for example.
Right.
Yeah. So, and there's still a lot of research that's going on, and in trying to understand, all of the things that's being stored in the embedding space, right? But for today, we're just going to roll with like this general this concept of, they will store knowledge and they will store things that are similar, whatever that means.
Yeah. Yeah, so question in the back?
Yeah, so I've never tried this, but if you had to take like GPT or any of your LLMs and then use like another language that's not as similar as English, would that cause like a massive problem for GPT? Like, because assuming that your grammatical structure is different, and if it's trained on mainly like the English language, and you don't have so much like training in like Swahili or some random language in like Africa, would that pose a significant like challenge to it?
Yeah, most definitely. Or just from a general language model perspective, right? When you train, that's how the model learns, right? The model learns by training. So of course, if there's not that much, or if within the model's training data there was not that much Swahili, then compared to English, right? Then the model may not have learned that much about the language. And then further, from a word embeddings perspective, right? So first, so assume that that within your vocabulary that you even had Swahili words, right? Because if you didn't, then the model might not be able to properly, it might not be able to understand what those words, what they even are, right? But say that it did, right? But if the model, and thus, if the model didn't have enough time to learn, what these embeddings meant, then they might not store, the best knowledge, right? The embeddings may not, be in the best places because they just haven't had, enough time or enough data to do so. So both of those factors could definitely have an impact. Does that help?
Yeah.
Before you move on, I want to be sure what do you mean by encapsulate
Right.
parts?
Right. So basically, notice that our embeddings, because the words that we learn have relationships between them, right? Like, for example, when we try to learn a language, we're trying to learn the language, we're learning the patterns behind that language, like we said, right? Like in kind of the way we look at words, right? We have certain patterns as to how these words are represented in our minds, right? Language is built upon patterns. So the idea is our embeddings should somehow show these patterns as well, right? They have to show that these patterns are embedded into these embeddings. So for example, over here, we can see that all the embeddings that we talked about before, all the embeddings for similar words are closer together, right? So we'll say that semantic similarity is encapsulated by this embedding space. Because the different embeddings in our vector space right here, they are indicative of the fact that they are influenced by these patterns. Right? So the way we think about this is, if there was certain patterns that we have in English language, then we want those patterns to somehow carry over to our embedding space as well. And it's only by doing that the model can learn and generalize to language. Make a little more sense?
Yes, thank you.
Lots of questions.
I get it. Yeah, we're good.
Okay, so how can we create word embeddings? Well, let's give it a shot, right? So say we want to make embeddings for the 20 words that we have, right? What's the easiest way to do this, right? Well, what if we just make each embedding 20 dimensions, and then for the ith word, we'll have a 1 in the ith dimension, in the ith place, and then 0 everywhere else, right? So say for burger, right? Burger is the 0th word. So for the 0th dimension, we'll have a 1 and then zeros, right? Batman, 9th word, and we'll have a 1 here at the 9th, and then 0 for the rest, right? And this is called a one-hot encoding.
Yeah, this is the simplest way. This is the simplest way that we can represent a word as a vector, right? Just assign it to some one-to-one arbitrary function, right? Some one-to-one function, right?
Yeah.
That maps from vectors or maps from words to vectors. Okay?
Yeah.
But the problem is that one hot represents each word as an independent direction in the vector space. Okay, each word is completely orthogonal to each other. If you think about taking the dog park, right? Each word is completely orthogonal to one another. So this means that there's no possible way that we can encapsulate any structure or pattern between the words. Forget semantic similarity, but before we have those green embeddings together, those purple embeddings together, there's no way we can encapsulate any patterns whatsoever in this embedding space, right? The dot product is always going to be 0. So there's no way we can have vectors that are close to each other, right? To indicate similarity. So yeah, they're always, you know, very poor at this. So we can do better than this.
Yeah, and so for the example, right? For example, say, you know, just for visualization, that you did one-hot encodings for a vocabulary with 2 words, right? So what does that mean? Well, you have one word 0, 1, but that's the vector. The other word's 1, 0, right? But however much you move in this direction on the y-axis will not impact
Any movement at all in the other direction.
exactly on the x-axis,
right?
So this direction has no impact in this direction. Therefore, we can't. There's no relationship that we can see between
That direction is.
Yeah, exactly. Yeah. Yeah. So So one hot encodings. They're unsophisticated and not the most effective, right? And this means that, effectively capturing the structures and patterns of language in high dimensional space. It turns out it would be very hard to do manually, right? One hot encoding is something that we can do manually. We can just, say that, okay, for each word, that's the one hot, right? But, say you have a 12,000 dimensional space and 30,000 words in your vocabulary, right? It's not very human to be able to try to assign, some vector to each word that can properly capture all of the numerous relationships that word has with the other words, right? So luckily we don't have to. Instead, word embeddings are learned by machine learning models, usually while doing some sort of task, which will automatically find the best vector for all the words.
Yeah, so as I said before, if it was semantic, or if it was, trying to identify the motion of a word, for example, it might group all the vectors like that. For example, it might learn that embedding space, right? Another task might learn a different embedding space, so on and so forth. Yeah. All right, are we good so far? Okay, cool. Okay, so let's try to wrap our heads around what the embedding space we just created is, right? So as these embeddings improve while training, right? As we get to learn these embeddings better, okay? The embedding space should reflect the model's understanding of the words, right? Like, for example, the whole point is that we would want our embedding space to look something like this, for instance, right? Where each vector represents, a different idea or like a different, token or a different word that we have. And we want it to basically be able to find an embedding space that's perfect for the task at hand, like we mentioned before, right? So like similar words that share similar semantics should all be grouped together, maybe even syntax, right? All plural words in this case are grouped together below the x-axis, and then all vehicles are grouped, back to themselves, to the left, right? And so on and so forth. So basically, the main idea is that we want to be able to have an embedding space that represents these learned embeddings. Yeah, if you want to add on. Okay, so when, oh, sorry.
Yeah, so when words that share the same or that share some level of meaning are grouped closer, then we're bound to see some patterns emerge in the embedding space, right? So for example, what patterns can we see here, right?
Yeah, I guess I gave it so that's my bad.
Yeah. So for example, we have that vehicles, as you can see, they're associated with the negative x direction, right? So we have cars, bikes, planes. Here we have various foods. Fruits are associated to the positive x direction, and plurality will increase as we go from top to bottom, right? So all these words here are singular, and these words here are plural, as we have here, right? And so these concepts of vehicleness, fruitness, and plurality are called our features. Okay, we have a quick
Yeah, let's try to look at a real life example of what this embedding space would look like in a trained transform model, and then see if we can uncover some of those, patterns for it.
exactly. Yeah. So this is a very neat website by TensorFlow. And basically here, so this is a so basically they had high dimensional word embeddings, and then they used some dimensionality reduction methods, which we're not going to talk about, but they used some dimensionality reduction methods to project those high dimensional vectors each to a 3-dimensional space. So now we can kind of see these word embeddings in 3-dimensional space.
So yeah, for example, we have, employee, owners, owner, private, lands, words like these.
And what we can see here is that there are these clusters, right? And the clusters contain related words. For example, there we go. Here this cluster seems to be of states: Dakota, Colombia, or states and locations: California, Texas, Dallas, right? We have a different cluster here, right? Yards, feet, meters, yep, distance, right? It's just to visualize sort of the different clusters that word embeddings can form.
And yeah, obviously these are n-dimensional space. We've shrunk them down to three dimensions.
Yeah. And you can all feel free to explore this website too later on. It's pretty cool. Right. Questions?
I think we're good.
All right.
Okay, let's talk more about this concept of features, right? So when we learn about features, early lectures when Rafi was talking about them, right? We learned that features are properties of our data that we can use to make predictions, right? So if you want to predict weather, for example, we have certain features. We might consider the weather data such as temperature, wind speed, precipitation, and we kind of combine these data for the features to create some inference upon them, right? In LLMs, we're going to define features much more broadly, right? So think of features as just concepts, just plain ideas that can be represented at all in embedding space. And secondly, think of features as directions in our embedding space. It's like before, going back to our example, or kind of back to this new example, we kind of have this direction that corresponds to numbers in general. And we have this other direction in our embedding space that corresponds to words. So things that are more words are going to be, to the top there. Things that are more numbers are going to be more to the left there, right? Yes.
For LLMs, are these learned or given?
It's a really good question, right? So basically the idea is that the LLM will learn like the features that, that will be used for the task at hand, right? There might be, we'll get into this on the next slide, but basically what you're talking about here is the concept of feature geometry, right? The structural distribution of the various, feature directions. For example, it might learn to associate that all numbers, should be in that, on words should be at the top left there. To associate that other things should be like in other places, for example, right? Yeah, that feature geometry, is learned.
Okay, now we move on to linear representation hypothesis. So evidence suggests that the embedding space has a more sophisticated structure, and particularly it's quite linear. So linear representation hypothesis is a phenomenon that's been very much observed, right? And basically, what it says is that number one, features are represented as directions in the embedding space, and this is an important point, because when we say directions, we mean the linear direction, right? Because one direction is just a line, like you go in that direction, right? Two is that you can linearly combine feature directions to create new features, right? And similarly, a feature may be decomposed into a combination of constituent features. For example, say here that we have this, just for example, this 2D space, right? And say that this direction here on the left is a direction for Paris, right? Well, we can subtract the direction for France and then add the direction for Italy, and we end up getting a direction that's very close to the one for Rome, right? Because basically the direction for Paris can be decomposed into the direction for France and the direction for capital, right? Just the concept of capital, right? Then of course you take Paris, you minus France, you get the direction for capital, then you add the direction for Italy, bam, that's now the direction for Rome, or very close.
Like you've taken the component of country away from a capital and added a different country to that capital. So now, if you think about in terms of features, you now have this component that's of a country, Italy, of a capital, right? So you're gonna get the Rome. And when I was talking about earlier, the idea that we can decompose, like when we have linearity, we can decompose like the vectors into these subordinate forms we talked about way back at the beginning of our lecture, right? This is the linearity that I was talking about. This is a linearity that makes things really easy for us to understand and interpret this embedding space. This goes beyond just semantic similarity and syntactic similarity, plurality, or meaning. This is actual structure to a certain extent of the embedding space. Okay, are we good so far? I think we talk about linear representation hypothesis and then the concept of what embedding spaces intrinsically mean and convey. Absolutely. Cool.
Okay.
Okay, so transforming embeddings, right? So the whole point is that as our model trains, the embedding space is going to undergo a lot of different transformations. Okay? The embeddings might shift around, they'll move around, okay? They'll get warped, they might even undergo some, tractable transformations, but the whole point is that our transformer transforms this embedding space into an optimal form for a task, okay? So for sentiment analysis, after learning and training on a certain language task, it will learn an embedding space that puts all similar emotion words together and clusters them like we see above, right? And the assumption is once the transformer can achieve this structure of the embedding space, it has understood language generally. So now we can take this and solve any general language task, okay? That relates to sentiment analysis. And then for next word prediction, perhaps all words with similar meaning should cluster together in order to predict the next word in the sequence, right? Like, oh, today is sunny, I am happy, versus today is sunny, I'm joyful. So perhaps joyful and happy should be learned to be placed together in the embedding space. So we really want to be able to teach you guys that the transformer's entire job is to transform this embedding space while it learns, right? Its understanding is evolving as it learns. And as it achieves a more enlightened understanding at the very end, it'll help it solve some tasks that are important.
And we do want to make a note that so when we say transform, there are actually two different kinds of transformations going on, right?
That's a good point.
So one is that what we've been talking about so far, right? We mentioned that the embeddings they're learned, right? So you can imagine that we're not going to get into the details, but you have some process for learning the embeddings, right? So you start off and they're random, and then through this training process, they're going to shift around, and they're going to they're going to end up with these learn patterns, right? So for transformers, right? So transformers, we're not going to really get into the architecture today, but they have different layers, right? And basically, the point of these layers is that you start with embeddings, and then these layers will transform the embeddings, sort of like how training transforms them too. Now, transformers are trained too, and the embeddings you usually train the embeddings that you start out with, the embeddings that the transformer uses before they go through the layers of the transformer. Those are trained too, so they're not untrained, but the transformer will do more transforming to get it to a final state that's more appropriate.
It's a good point to make. It's good. Okay, so
All right, now we have a live demonstration.
this is a really exciting live demo that we have. Or first of all, do you have any other questions about anything we discussed so far today? And this is a really exciting live demo because this is completely self-made by me and Alex. So we basically taken a transformer model, deconstructed it, and modified the actual code so that we capture the embedding space at every single layer of the model. And this is kind of like our little, like version of seeing how the model's embedding space learns and changes over time.
All right.
Sorry, okay, I want to ask you, what does mean the classes?
Oh yeah. So okay, the ones that we have here, basically we have this sentence, right?
So our sentence is not really a sentence.
Yeah.
It's just 1, 2, 3, 4, 5, 6, 7, 8, 9, red, blue, green, orange, all these different similar words
It's a
together,
string, yeah.
right? It's
Yeah.
a really large string.
Yeah, yeah. And then the
And
classes.
then you create a list of those string
Or-
So each class would kind of be like each category, right? For example, like fruits, or berries, for example, would be like one class,
Yeah.
right? So on and so forth. The assumption is we want to kind of see if it would cluster different,
Yeah, and so for example, like the purple ones here, these are the foods, fish, chip, or no, they're animals. No, chip, I think is chipmunk. It got split into chip and monk.
Chipmunk got split, tokenized into chip and monk.
Yes, okay.
Yeah.
But it is an animal.
Not necessarily foods. The light green one, those are months.
Yeah,
right?
March, July,
Yeah.
so on and so forth.
So, and now the question is, so these are the embeddings of the words as they start out, right? But then as the embeddings go through the model, go through the layers of the transformer will transform them, and we will see this now. So yeah, so one thing to note is that a lot of information will be lost here, because basically what we've done is we're using dimensionality reduction to project 64 dimensions, which is the true dimensionality of these embeddings, down to 2, right?
Two-dimensional space,
So
right?
for us, it's not totally clear, I mean, there does need to be a little bit, of some clustering.
There's some decent,
Yeah,
there's some clustering.
green's
Some-
here, blue's here, but we are reducing actually most of the information because we're switching 62 dimensions down. But just imagine that in 64 dimension space, these embeddings have clustered in some way that is more useful for the task.
Right. Cool.
Oh, yeah. That's it.
So any questions about anything we talked up till now? Yes.
Why did they spread out?
What do you mean
Like,
spread out?
why did it look like they all got generally closer together?
It's a good question.
Yeah, that's a great question. That is, or the explanations for that goes a little bit more into like the specifics of how things work, or like how the model works. And we're not going to totally cover that right now. But it's basically okay, but I'll give a little bit of information, right? So a big task of the transformer is to bring context between words, right? You start off with embeddings for individual words, but the embeddings know nothing about the rest of the words in the sentence. A huge job of the transformer is to bring that context between them, right? Because you want to understand the whole sentence, not just each word individually, right? And it turns out that by doing it, it kind of makes them more similar, which means they'll get closer. Yeah, good.
Bringing
Yeah.
similar words together, we're basically bringing those directions together, so we're kind of condensing it a little bit.
Yeah.
Yeah.
Right.
Yeah.
What was your thing string of like data?
Right, it's tiny stories, right? So it's a collection of children's stories, right?
Yeah, but that wouldn't really matter for, or
Yeah,
just like for the idea.
Yeah.
Yeah, the reason we used it is because basically models that are trained on tiny stories, it's been shown that they can be really small, and we wanted to use the smallest model possible for simplicity reasons.
Cool. Okay, and then I guess, yeah, this is a quick key takeaway slide, make sure you understand everything. We got one more slide for this and we'll be wrapped up. So first thing, transformers are the fundamental architecture behind LLMs. Language models are any models that perform language tasks. LLMs represent words as learned embeddings or as high-dimensional vectors, right? And this embedding space has a lot of really neat properties and a lot of neat patterns that help it to train and understand the context better. And the transformer's entire job is to shift and work this embedding space to solve a given task. Cool. And then one final note is today we kind of learned about different things that an embedding space is able to represent. Okay, so an embedding space, we talk about how it represents semantic similarity, words that mean things are closer together, right? Words that mean the same things. And then syntactic similarity, words that have similar grammar or move together. And the frequency of the words, right? For example, words that appear very close together might be close together, like Alex Ning, right? They're two separate words. And then linearity, right? We talked about linear representation hypothesis, how we can see that structure in the embedding space. But there's one really important concept that this embedding space fails to capture. Okay, and that's the idea that the meaning and understanding of words can shift dramatically based on how we use it and the context that we use them in. For example, if I had two sentences, I went to the river bank versus I withdrew money from the bank. The entire meaning of the word bank and this bank are two completely different things in our minds, right? But based on everything we just talked about together today, it should group those two things very close together in the embedding space because they are the same word. And we don't use anything else about the word other than the intrinsic word itself and the task at hand, right? In other words, our current embedding space has no way of capturing the context of a word in a sentence. And if we want to do a lot of really, really cool language tasks, we want our embedding space to be contextually aware, okay? So I guess, yeah, we'll cover this in much more depth in the next lecture. But yeah.
That's it. Thank you very much. And
Thank you guys.
yeah.